Swayam Prabha. Digital India. Educated India.
Welcome to the lectures of this course on Foundations of Cyber Physical Systems. So, I believe in the last lecture we have been discussing about different kind of sensors and the physics behind how those sensors operate, of course at a very high level. So, continue from there. So, here is just a simple example of an actuator. So, it's basically the hydraulic brake booster, which is very much standard in anti-lock braking systems in automotive. Now, all of us are quite aware of the physics principles how in a hydraulic system you have liquids which can amplify the pressure, right? So, this braking principle of the actuator is primarily based on that. So, here of course we are not showing the electronics involved around this kind of a system, and this is a very high level picture. Of course, you can understand that this foot pedal, the application of the final brake will be controlled by an anti-lock braking software. So, it's not going to be a direct connection like this, but this is a very simplistic example here. So, we are just trying to have a high level view here, right? So, how an hydraulic brake works, I think it's now very much evident from this elaborate picture here. So, as you can see that all these four wheels of a vehicle, they would be connected by these pipes, and these brake pipes will be containing an incompressible liquid here, right? And that liquid network is having a master cylinder on which the piston coming from the foot pedal will be connecting. Now, I will just repeat that. Of course, in the age of software where you have anti-lock braking controllers, this is not going to be a direct connection like this. So, what happens is in this simplistic example, when you put some pressure on the pedal, that pressure will be kind of moving on to the liquid, right? And that same pressure inside the system will be magnified quite a bit when it actually gets applied in the brake pads. So, this amplification will actually make your car to halt, and you can understand that the actual amount of force required for bringing the vehicle to halt is much more than you are applying physically here, and this amplification is happening due to this hydraulic system that you have. So, essentially that's how the physics behind the actuator works. Now, in a software control system, what would happen is this physical actuator, its movement, when it will engage, when it will disengage, those things will actually be controlled by suitable software control signals, and that's how an anti-lock brake works, that it decides that how many times to brake and then engage and disengage this master cylinder piston, so that the vehicle doesn't slip over tricky surfaces. So, again, this is a high level view, but it provides you with an accurate enough example of how an actuator works, because you can understand that this would really mean that the real pressure on which this system can operate, that will have a lower bound and upper bound, okay, and that would also mean that the software signal that should come in a real life ABS, that should also have lower bounds and upper bounds, and that will be the variable bounds inside which a practical brake pressure should be available. Now, the other important thing which is like apart from sensors and actuators and control softwares we have been talking about, we need to think about that how they really operate together, because as you understand that this is a physical system, whereas the control signal that would be coming to give the actuation command is a digital command, right? But this physical system will of course be actuated by some analog values, and similarly for most sensors, right? So, any sensor will generate an analog signal, right? And that signal needs to be converted to a digital value when that signal needs to be read by a digital computer, right? So, this lands up to this requirement of what is an ADC and what is a DAC and how do they work. Again, that's parts of our electronics course, but again here we will be just having an overview. So, thinking from the sensor side, so sensors are generating analog values, and those values needs to be converted to a digital equivalent, and that has to be done through an analog to digital converter. And there are these ADCs have different kinds of algorithms. So of course the real ones that are used will have will be very sophisticated. We'll just touch upon some simple ADC DAC circuits and how they really work. So let's take an example here. So here we have an example of ADC algorithm, which of course will be implemented in a hardware, and let's understand that how I can convert this analog signal to a corresponding sequence of bits which will be transmitted to a digital computer. So the idea here is of one of successive approximation. So what happens is, suppose we are trying to approximately represent this analog value. Okay, so what we start doing is we are trying to build the corresponding digital equivalent. Let's say a 4-bit digital equivalent. So first thing we will do is we will set the MSB to 1. Okay, and we will see that, well, let's call this signal V minus. Okay, and let's see that now let us compare whether this signal is greater than or less than the target signal which we are trying to approximate here. Okay, now we see that this is less than the target signal, so we will now set the next bit to 1. Okay, now once we do that, we find that, well, now the signal, the digital equivalent signal, is becoming higher, right? So we are comparing and we are finding out that this is higher, right? So once we find that to be happening, then we will unset it, and we will just so you see that this 1 has now been changed to a 0, and we go to the next bit, next significant bit, and we will set it to 1. So this is done, and now I find that, well, it is again lower than the target value. Then I will again set it to the corresponding, then I will just move on to the next bit, and I will set it to the higher. So then this is the best approximation I can get of this target signal using this 4-bit representation, and that will be my output. So of course you can see that this is going to work on multiple clock cycles when I am going to use this in real life. Not only that, at every point I would need a DAC, because I am going to convert this to a digital equivalent, and not only that, I will need a comparator, right? So if I try to create this circuit, it should be something like this. Let us try to draw this circuit here. So you will need a comparator here. So the logic that I explained of this generating this bit pattern, let's say it is implemented here in the digital circuit. So, and that output comes here, then a D2A comparison happens. A D2A conversion happens. And then it goes to this comparator. So you have an operational amplifier which is a kind of working as a comparator here, and you are taking the decision whether to set or unset the current bit, and and moving on to the next decision here in the bit pattern generation logic. The important thing to note here is, well, we are using a D2A chip here inside anyway, right? The thing is, that's an easy to implement thing. Okay, the ADC logic implemented in this way hence becomes one option. The issue with this kind of a circuit is it can I mean I can run this circuit at high speed and it can work well, but of course one thing we observe that the the A to D conversion in this case will take multiple clock cycles. If I am going for an n bit representation, generation of the final bit pattern for each analog value will need n number of clock cycles here. So that's the problem. Okay. Now, is this the only option? No. I can also have what we call as a flash A to D converter. Okay. So that means in one cycle, and instantaneously, without having to go for multiple clock cycles, I would like to have this kind of a pattern generated for a given signal. So let's see how that can be done. So suppose I employ multiple such comparators. So as you can see, there is a reference voltage, and so this is the reference voltage, and we have this voltage Vx, right? And what we are doing here is we are having a voltage divider network of this resistance. It has four resistances of the same value R, right? And this is kind of dividing this voltage Vref into four possible values, right? So now when you try to do the comparison, you see so these comparators are going to generate a bit pattern depending on the value of Vx and how it compares against Vref, how it compares against Vref by 2, how it compares against Vref by 4, and how it compares against 3 Vref by 4, right? So accordingly, these output bit patterns will be sensed, and there would be an encoder circuit here which will be having these decisions that whether Vx is greater than or less than Vref, and similarly being compared with 3 Vref by 4, Vref by 2, Vref by 4, and all this. Accordingly, you will have 4 decisions here. Okay. Now, it will be the job of this encoder to kind of convert these individual comparison values. I mean, from this point it becomes a simple digital encoder design problem, right? And that would generate the final bit pattern. What is the advantage of this scheme? Definitely it would work in a flash, right? Because I mean, there is no requirement of multiple clock cycles or everything. So that's why this has a name. It's called flash A2D converter. What is the disadvantage? Well, it requires more hardware resources. For example, it will require here in this example you are requiring 4 comparators instead of using one single comparator in a serial manner when you generated that successive approximation signal, right? So that's one alternative here for you. Now coming to DACs. So when we talk about these ADCs, they are going to take the sensed analog values and they are going to generate signals for the computer where you have the control law implemented. But then when your control law computes that control output, it is again in a digital form as an output of the computer, and this needs to actuate some analog action, right? So you need to convert to an equivalent analog value. So typically this actuator would be driven by a voltage, and that is converted through this DAC, and the voltage should be proportional to the digital signal. Okay. So how this can be done? The idea is that if I can have a converter which will first generate a current that is proportional to the value of the digital signal, and then I have the equivalent voltage generated. So this is one possible simplistic example of a DAC circuit, and I think it is fairly easy to figure out how it's going to work here, right? So for example, what are we having? We are again having a operational amplifier here, okay, with the input, let's say, I mean, as we know, typically for an op amp, this difference in voltage is kind of approximately, I mean here this is connected to the ground, here we are giving this VREF, right? So what is happening is this input bit pattern will be used to turn on or turn off the switches. So you can think that these switches, I mean, what they are really. So they can be just MOSFETs, right? Where whether the bit where the bit pattern once it's high here, it will lead to this gate being I mean this MOS which is acting as a pass transistor. So it will just act as a switch and it will turn on, and this connection would be sorted from the drain to source, right? So that's how these switches are modeled, and accordingly what would happen, the current would flow through this resistor network. Now observe one thing, the value of the current that will flow here, okay, that will depend on this resistance network, and as you can see in this case, this resistance values are chosen like R, 2R, 4R and 8R, right? So it's basically based on the binary weightage of different bits, right? So if you apply standard Kirchhoff's laws here, you will see that the current values are accordingly, I mean dividing this voltage proportionally and taking their corresponding values here, right? Now what this means is, whenever you allow the current to flow, it will the amount of current that flows will really depend on the weightage of the bit, right? So when it's LSB, you have I mean the current VREF divided by R times 8, right? So that's how the weightage is. So if I sum up the total current that is coming here, what do I get? It should be an expression like this following the current's law, right? So you have this kind of an expression. So if you take common this VREF by R, you will have something like Xi and I minus 3 to the power, right? Because let's say you take X3, you are essentially allowing this full current to go, right? Basically VREF by R to go. If you are taking the LSB, you are allowing the least current, that means Vref by 8R you are trying to you are letting it go, right? So since it's the least significant bit, the amount of current allowed is the least. That's why it's, that way it is modeling the weightage of the bit, right? So in that way we have a proportional amount of current generated. So in that way this bit pattern is getting kind of transformed into a proportional amount of current, right? So when you have a proportional amount of current moving here, when I apply it through this operational amplifier network, right? So I will get a proportional voltage generated here at the output, and that would be my analog equivalent, right? So you can see that I can just apply Kirchhoff's current law here to this node that is connecting like this, right? And what will happen is I will get this proportional voltage, because this will form a standard voltage divider network here. So this is about a very brief overview of DAC and ADC circuits that we have, right? So a very standard way to derive these equations, like you see, all we have done is we have applied this Kirchhoff's voltage and current laws in different points, although I try to explain it in a more simpler way, just adding the current values and all that, fine. So we understand how basic DAC and ADC algorithms work, but let's understand one thing also, that even for an analog signal, when I am generating the digital equivalent, am I really generating it for all possible analog values? Not really, right? So let's say you have an analog signal which is changing its value like this, right? So what I am doing is I am sampling this signal, let's say from the sensor itself, okay? So I am actually sampling this signal with a specific periodicity. So I am sampling this value, then I am sampling this value, and I am sampling this value. So these values represent to me the signal information which is sampled periodically, right? And that is what is the analog value which will be given to the analog to digital converter to convert and send it to the digital computer, right? And of course the digital computer's converted value computed value in the digital domain will again be activated by a DAC chip once every period of age, and it will be applied to the actuator. That's how we have a sampled data a sampled data system which is there acting as an interface between the plant, which is analog, and the controller, which is in the digital domain. So overall we have this kind of a cycle. You have the plant measurements, which maybe, here we have a difference in different cases. So either there is a sensor which is attached, which is doing continuous sampling, and then so the sensor is continuously reading the analog value, and that value is being sampled periodically, and then those sampled values at periods of H, they are given to the ADC. Then the rest we already know. The controller is going to compute the output available for control. This output will be sampled or read from our output buffer at a periodicity of H, and then that will be kind of converted to an analog equivalent, and that will update the actuator circuit's input at the same periodicity. So the DAC will also work at a period of H. The output of the DAC will update the actuator's input value with an analog signal at a periodicity of H. This sampler, which will be reading the controller's output, will do the sampling at a periodicity of H. So in an ideal control system, that's how it will work. Everything is very regular. Plant is getting sampled, or the plant is, so like I said, there are two options. Either the plant is continuously sampled, continuously a measurement is generated, and that measurement is sampled to generate these analog samples, and then those analog samples are converted to digital samples. So at this point what you get basically is a stream of digital data. These are all separated by this period of H, right? Before this, it is either like you are activating the sensor at intervals of H, or like I said, the sensor is continuously sensing, and the sensor's values are sampled at periods of H, and finally you have the DAC, right, the ADC here, and then here this control output is sampled. Then the DAC chip will be clocked with the period of H, and it will update the actuator's control input with the period within a period of H. Okay. Now the question is, how does this kind of sampling happen? Like, let's say the sensor is continuously sampling. Let's say the sensor is continuously taking the measurement. So it is generating a signal like this. But like I said, I am going to read the signal only at this kind of specific points, right? So one idea of doing such sampling would be something like this. You can have a very simple sample and hold circuit. So let's say here the continuous signal is coming, and there is a pass transistor here. The output goes to a capacitor, and I am actually reading the voltage across the capacitor. So now what would happen is this pass transistor is activated by a clock which is sending a positive edge at a period of H. Okay, again at H, so let's say here these positive edges, they will have a periodicity of H, right? So this will be closed, or maybe I do a different kind of diagram here. Let's say there is a short pulse happening here, then a short pulse happening here. Okay, so that would mean when the gate closes, the capacitor will charge very fast, right? So let me again draw the analog signal like this. Okay, so the gate has closed, let's say here, right? So at this point, till now the capacitor's input was kind of here there was no charge, let's say. Now at this point, when the gate closed, it slowly built up the charge. So the output right now is this, and then it is kind of almost constantly holding the charge. Very minor decay would be here, right? And then at this let's say at this point it is sampled again. Okay, So then here from this point it will again start and get the charge again, and then again it will try to hold the charge. So in this way it's basically sampling almost in a small amount of time, depending on the time, depending on its capacitance value, it will get the charge and it will hold the charge almost with very small decay up till the next point, and from the next point again it will, depending on the voltage there, it will again lose or get further charge, right? So that's how a sample and hold circuit will work. Of course this is a very simple example I am showing you here, and it will give you a set of those sampled analog inputs, and those sampled analog inputs are going to drive your analog to digital converter, and then at the output I will get a bit stream at a periodicity of h. Now of course in our previous week we have kind of discussed about different kind of CPU compute platforms, and just to summarize its properties, like we want such CPU compute platforms to be very low power, and what are the usage of those platforms? Of course you are going to do the control law computation, but that is not the only use. It will be also used for many real-time algorithms. For example, whatever sensor data you are getting, that would be noisy, so filtering the data, using the sensor measurements to do state estimation of the plant variables, and maybe you can also run some ML pipelines to do some recognition of identifying interesting features from that sensor data, right? And finally you can also compute the control law. So all those things have to happen here, and it has to happen following an important characteristics, which is that the compute platform should be low power. So like typically they are RISC CPUs and microcontrollers which are being used for this purpose, like we have already seen in our previous discussions. Now what about the communication? So whenever we are talking about the cyber physical systems, we have said that, well, communication plays an important role and the communication has to be real time, right? So let's take an example. Consider that how in a modern vehicle you will have so many control loops, and those control loops may be implemented in different ECUs, right? And those ECUs will need to exchange messages among each other, right? So and that message exchange can typically happen at a very high rate, okay? So it can be in the order of, one message per 10 millisecond, or one message per 20 up to 30, up to 400, like that, okay? So a 10 millisecond period kind of that represents a big high rate in the kind of network protocol that is followed inside an automotive. So the issue is, if I have many processors, so any modern automobile can have 50 or 80 ECUs inside them, of different form factors, okay? Now the issue is, if I try to connect each of them, right, all possible pairs, right, it would be an order n square number of wires that I would require, right? And that would be a big mess. So we understand that there needs to be a standardized bus architecture which needs to be followed whenever you are connecting ECUs, right? And for such bus architectures you need to have a suitable communication protocol that would ensure lossless but fast data transmission. Unlike our standard TCP/IP kind of protocol where it can also be lossy, this has to be lossless, and even if there is a loss, it should be immediately detectable, and it should meet the real-time guarantees, okay? Even if there is a delay, there should be a good worst case estimate of that delay, not a probabilistic estimate, but a better one actually. So all of these are properties that would be required to be satisfied in an automotive system, and also it has to consume very low bandwidth, and it should not take too much power, right? So essentially you need to have a very simple network protocol, some protocol which doesn't require too much of a network infrastructure, lot of switches, nothing like that, because this would be inside a car and it should be as low cost as possible, right? So in this way, the most commonly used protocol that we have in automotives is called control area network, or CAN bus, okay? So this is the de facto standard in automotives, though nowadays automotive Ethernet and other standards are also coming in, but this is still this happens to be the de facto standard for all intra-vehicular communication. This was developed by the company Robert Bosch around 1980s, and the current version is 2.0 from 1991. And of course, there are new variants of CAN that have come up, like CAN with flexible data rate and other variants. But what we will do is we will study the basic protocol, because that is pretty much used till date. So, how does the CAN network work? So, the basic idea is that all the nodes that you have in a CAN network, they will connect to one common bus. Okay. So, they will connect to a one common bus. That means all the nodes kind of they are always looking into what data is there inside the bus. Okay. And any new node can be added to the network at any point of time, even if the network is online. So, it's hot pluggable. Okay. And whenever the bus is free, any node can send a message. That means for sending messages, a node doesn't need some master node's permission or stuff like that. So that is not required at all. So no such thing exists there. Okay. And so this is called a multi-master thing. There is no master node or something like that. And the other thing is, it's also multicast. That means all nodes may receive or act on a message. That means whatever some node is sending, everybody can actually see. It can actually read also, right? Now, the way a CAN network is designed is very simple. Basically, it's a twisted pair cable. So, since it's a twisted pair wire, so that also makes it resistant to electromagnetic interference. Typical payload size, that means the actual data that is used, is a very small packet. It's a 0 to 8 byte data. So, this also means that you cannot do some bulk data transfer. The packets are quite lightweight, if I compare to standard network packets, but at the same time that also makes them perfect for most embedded control applications. The bandwidth offered by this kind of a network is typically 5 kilobytes per second to 1 Mbps. Now, of course, the bandwidth has a limitation on the cable length. We can understand that from simple physics here. So, if you are trying to afford 1 Mbps speed, your cable end-to-end length should be inside 40 meter. Similarly, for some limit for 40 kbps, a slower speed, higher range, something like 5 kbps, much slower speed. You can have a much bigger cable. Of course, you don't need this much bigger cable inside an automotive, but you can have a few kilometers of cabling inside an automotive, which is kind of which always happens, right? So these interfaces are usually pretty smart. You have every CAN node will have a CAN controller, and these are the CAN interface through which the node will connect to the bus. So this can be interrupted only after an entire message has been received, and it can also filter out unwanted messages, so that problem does not go to the CPU. Nowadays, what happens is many these microcontroller units that are available in the market, they actually have onboard support of CAN. That means they have the CAN controller, and you can just connect the CAN wires with them. So that possibility also is there. Now, CAN doesn't specify a physical layer. So that means unlike other transceivers, the physical layer is not implemented, but there is a choice, and the standard choice that designers take is a twisted pair with differential voltage. That means there are two cables, they are twisted pair, and the current is flowing in each signal line with equal but they are opposite in direction. So that's kind of balanced, and there is very low noise emission, and due to the twisted pair setting, it's very much resistant to noise. And because think of a vehicle's bonnet, there would be a lot of noise, there will be a lot of disturbances, and your bus needs to work inside it itself, right? Every node, when they transmit, they can also listen at the same time. They can see what is getting transmitted, and they are always able to listen to the channel even when they are kind of transmitting. Okay. Now the CAN nodes are the way they are designed. They are very cheap actually. They permit every node on the bus to talk, and the interfaces, the CAN interfaces and the transceivers, they are very cheap actually. Okay. And as you can see, the number of CAN nodes sold in different regions. This is a pretty old statistics, but still it's quite significant. I mean, because CAN is kind of de facto standard in automotive, and CAN is used also in several other industries. Okay. So like we said that everyone on the bus can see that what bit is getting transmitted. Okay. So and that's one important point, and this has a significance. We will soon see that how, if two nodes with different priorities are going to transmit, then how that arbitration, that who will finally be able to transmit, how that can be done. This has a very elegant solution in CAN. We will see that. One important point to note here is such things are not there in Ethernet. So what I mean, let me just explain. Suppose there are multiple CAN nodes who are trying to send their individual messages exactly at the same time. Of course, in Ethernet that is pretty much allowed. Only thing that will happen is that this will lead to a packet collision. Now, once this Ethernet in the Ethernet type connection, this collision is detected, there would be an exponential backoff, and in future probabilistically at some time point they will again try to do the data transfer, right? So we don't have any guarantee, but due to the high bandwidth that Ethernet provides, the packets will eventually get transmitted with some tolerability there. In CAN we have a bandwidth issue, hence we need an efficient arbitration scheme, and not only that, there should be a real-time guarantee. What we mean is, whenever this case arises that probabilistically multiple nodes are trying to transmit exactly at the same time, there should be a well-formed rule in place in the protocol which will say exactly who can transmit and exactly who cannot transmit, and that should be followed, and accordingly the nodes must behave. Okay. Now, so that's an important thing. We will soon see that how this kind of arbitration is done, and this also makes CAN synchronous. That means every node, I mean on the bus, every node, I mean if they are trying to send, the bus is operating kind of in a cycle-wise manner. So I mean if two nodes are transmitting, I mean it's either they are both bits they are trying to send at the same time or in different cycles. Okay. Now let us look at the time per bit discussion we had. We told that, well, there is a relation between how much speed I can have and what is the length of the CAN bus, something like that, right? So typically the speed of electrical signal propagation is like this 0.1 to 0.2 meters per nanosecond. Okay. So if I am having a 40 kilobits per second CAN bus, if that is the data rate, that means you are sending 40 into 1024 number of bits per second, right? So that means for each bit the amount of time you are keeping reserved is 25,000 nanoseconds. So inside this 25,000 nanoseconds, the distance that this bit may travel will actually limit the physical length of my cable, right? So that is why a bit can travel as per the speed of electrical signal we discussed, this much distance, 2500 meters. So accordingly we will keep a bus length which is less than half of that, so that this delay doesn't create any problem, right? Similarly, if I have a 1 Mbps CAN bus, so again so that's a higher bit rate. So for a higher bit rate we will have 1000 nanoseconds, a smaller amount of time per bit. So bit will be able to travel less amount of distance, and that will again limit the bus length. So with this we will end this lecture. We will resume from here in the next lecture. Thank you.